Ever wondered how a computer that leverages the mysterious world of quantum mechanics would function? Well, let's take a journey into the realm of quantum computing, where the traditional rules of physics are tossed aside, and the peculiar properties of quantum mechanics take the center stage. In the realm of the tiny physical matter behaves quite differently. It exhibits properties of both particles and waves, a phenomenon that leaves us in awe and wonder. Now, imagine a computer that could harness this dual nature. That, my friends, is the concept behind quantum computing. At the heart of quantum computing are two key concepts: quantum superposition and entanglement. Quantum superposition allows a quantum particle to exist in multiple states at once. It's as if you're both at home and at the cafe at the same time. Quantum entanglement, on the other hand, is a phenomenon where particles become interconnected. Any change in one particle instantaneously affects the other, no matter the distance between them. These characteristics provide the foundation for quantum computing. Specialized hardware supports the preparation and manipulation of quantum states, allowing quantum computers to perform calculations in a way that classical computers simply can't match. The potential of quantum computers is staggering. They could perform some calculations exponentially faster than any modern classical computer. Imagine breaking widely used encryption schemes or aiding physicists in performing complex physical simulations. The possibilities are endless. However, before we get too carried away, it's worth noting that quantum computing technology is still largely experimental and impractical. There are several obstacles to overcome before we can reap the full benefits of this technology. The creation of high-quality qubits, the basic unit of information in quantum computing, is a significant challenge. They must be sufficiently isolated from their environment to prevent quantum decoherence, which introduces noise into calculations. It's mind-boggling, isn't it? However, this technology is largely experimental and still faces many challenges. Yes, the quantum conundrum is as fascinating as it is complex. But as we continue to unravel the mysteries of the quantum world, who knows what incredible breakthroughs the future may hold. In the heart of quantum computing lies a new kind of bit, the qubit. Just as a bit is the fundamental unit of information in traditional computing, a qubit is the cornerstone of quantum computing. But what sets a qubit apart from a regular bit? Well, in classical computing, a bit can either be a 0 or a 1. It's binary, it's black and white. But in the quantum realm, things aren't as straightforward. A qubit can be a 0, a 1, or both at the same time. This is known as superposition, an inherently quantum mechanical property. Imagine a coin spinning in the air. While it's in motion, it's neither heads nor tails, but a blend of both. It's only when it lands that it adopts a definite state. That's a bit like how a qubit works. But here's the twist. When you measure a qubit, you don't get a blend of 0 and 1. You get a definite answer, either a 0 or a 1, with a certain probability. This is what makes quantum computers non-deterministic. Unlike classical computers that follow a set path to arrive at an answer, quantum computers can explore multiple paths at once. They're like navigating through a maze with the ability to go down every path simultaneously. But what's the point of having a qubit in a superposition state if you only get a 0 or a 1 when you measure it? Well, the power of quantum computing lies not just in superposition, but in the ability to manipulate these superpositions. By carefully crafting a series of quantum operations, we can guide our qubits so that the wrong paths cancel each other out, and the right paths reinforce each other. This is how quantum algorithms work. So, you see, while a classical bit is like a single note on a piano, a qubit is more like a chord. It has complexity, it has nuance, and it has the potential to revolutionize computing. Just as the manipulation of bits forms the basis of classical computing, the manipulation of qubits forms the basis of quantum computing. Creating high-quality qubits is no simple task. It's a challenge that's both fascinating and frustrating. And why is that, you might ask? Well, the quantum realm is a delicate place. The qubits, which are the basic units of information in quantum computing, need to be engineered with precision. They are not like the bits in traditional digital electronics. A qubit can exist in a superposition of its two basis states, making it a far more complex entity. Now, here's where the real challenge comes into play. If a physical qubit is not sufficiently isolated from its environment, it suffers from what we call quantum decoherence. This is a phenomenon that introduces noise into our calculations. It's as if you were trying to solve a complex mathematical equation while someone is constantly changing the numbers. It's disorienting and makes accurate computation nearly impossible. But here's the paradox. While we need to isolate our qubits to prevent decoherence, we can't perfectly isolate them either. Why? Because quantum computations typically require us to initialize qubits, perform controlled qubit interactions, and measure the resulting quantum states. Each of those operations introduces potential errors and suffers from noise. It's a bit like trying to have a conversation in a noisy room. You can hear the words, but the background noise makes understanding challenging. And in quantum computing, such inaccuracies stack up, turning a minor nuisance into a major roadblock. You see, the quantum world is a delicate balance. Too much interaction with the environment leads to decoherence. Too much isolation leads to errors. It's a fine line we're walking, and navigating it requires a deep understanding of both the quantum and classical worlds. It's like threading a needle in a hurricane, all while balancing on a tightrope. It demands precision, patience, and a whole lot of ingenuity. In the end, harnessing the power of quantum computing is no easy feat. It's a world filled with paradoxes and challenges that are as fascinating as they are frustrating. And yet, despite these hurdles, the potential rewards are too great to ignore. The quantum world is indeed a tricky one to navigate. So, why bother with quantum computing when we have classical computers? That's a question that may be on your mind. It's true that in principle, a classical computer could solve the same computational problems as a quantum computer, given enough time. But here's where the quantum advantage comes into play. The quantum advantage isn't about whether a problem can be solved, it's about how quickly it can be solved. This is where we delve into the realm of time complexity, a concept that measures the amount of computational resources, specifically time, an algorithm needs to solve a problem. The quantum complexity theory, a branch of theoretical computer science, shows that for some carefully selected tasks, quantum algorithms require exponentially fewer computational steps than the best-known non-quantum algorithms. Imagine a massive maze, and you're tasked with finding the quickest route to the center. A classical computer would start at the entrance and explore each path one by one until it finds the center. Now, this might work fine for a smaller maze, but as the maze gets bigger, the time it takes for the classical computer to find the center increases exponentially. On the other hand, a quantum computer, due to the phenomenon of superposition, can explore all paths simultaneously. It's like having an army of explorers at your disposal, each taking a different path. This allows it to find the center of the maze exponentially faster than a classical computer. But here's the catch: this quantum speedup is not universal, or even typical across computational tasks. Basic tasks, such as sorting, are proven to not allow any asymptotic quantum speedup. Additionally, the tasks that do benefit from quantum speedup are often highly specific and complex, and not the kind of tasks most of us do on our computers daily. Yet the potential of quantum computing is immense. If we can harness its power, we could revolutionize fields like cryptography, optimization, and even drug discovery. Quantum speedup is not universal or even typical across computational tasks, but the potential it holds is immense. The journey towards functional quantum computing has been long and full of hurdles. Our tale begins in the 1920s, when quantum theory first emerged. Scientists were grappling with a perplexing conundrum. Matter at atomic scales exhibited the properties of both particles and waves. This wave-particle duality was a radical departure from classical physics, and it demanded a new kind of understanding. This was the birth of quantum mechanics, a field that would later become integral to the development of quantum computing. As quantum mechanics was taking its first steps, another revolution was brewing: the advent of digital computers. In the decades that followed, these machines would transform every aspect of our lives, from business and industry to science and entertainment. Yet, even as they reshaped the world, they remained grounded in the principles of classical physics. The binary logic that underpinned these computers was a stark contrast to the probabilistic nature of quantum mechanics. For many years, these two fields, quantum mechanics and computer science, formed distinct academic communities. There was little overlap between them, and the idea of a computer that could harness quantum mechanical phenomena seemed like the stuff of science fiction. But as we ventured further into the 21st century, the boundaries began to blur. Scientists and engineers started to see the potential of quantum mechanics to revolutionize computing. The concept of a quantum computer, a machine that could operate exponentially faster than any classical computer, started to take shape. The qubit, the basic unit of information in quantum computing, was born. The journey towards functional quantum computing had begun in earnest. Yet, as we've seen, this journey is fraught with challenges. From engineering high-quality qubits to minimizing quantum decoherence, the road to a scalable, practical quantum computer is paved with obstacles. But every challenge brings us one step closer to realizing the immense potential of quantum computing. The journey towards quantum computing is ongoing, and the destination promises to be worth the challenges encountered along the way.